Good morning. I am Francesco Galvagno from the Torino University. I would like to thank the organizers of the Cortona Young Conference 2020 for this opportunity. And today I would like to discuss large charge as a possible dual Toft limit, which is based on this paper done in collaboration with Matteo Beccaria and Azim Hassan from the Lecce University. And I would like to invite the people to see also the talk by Azim Hassan. So we can start with an introduction. It is well known in a quantum field theory context that gauge theories with n colors admit a Toft limit which corresponds to take the number of colors n going to infinity, keeping this combination G square n fixed, where G is the Young-Mills coupling. This limit selects a specific class of Feynman diagrams, which are classified based on their color factors. In particular, as we see from this sketchy picture, only the planar diagrams are selected in this limit, whereas all the non-planar diagrams are dropped out. Already at this level, we see the importance of the topology of the diagrams, and this is crucial for the analogy with the string theory worksheet expansion, which is very well known and used in ADS-CFT context, for example. In this presentation, we concentrate on a different sector of gauge theories. In particular, our setup is the following. We consider four-dimensional n=2 super-conformal field theories, even though we are not going to use too many technicalities related to supersymmetric theories. And we consider the insertion of chiral operators, which have this shape, where phi is a scalar field, with large dimension J. This is important. We evaluate the two-point function between a chiral and an anti-chiral operator, like we see here, and conformal symmetry fixes the two-point function to be of this shape. In particular, the kinematic factor is completely fixed. We are left with this AJ, which is the two-point coefficient, and we want to evaluate this two-point coefficient at the level of perturbation theory in a new double scaling limit, which is defined as following. We take this dimension J going to infinity, keeping this time G squared J fixed. So this is quite similar to the usual large n limit, but in this case, it is the dimension that goes to infinity. This limit has been investigated in several contexts recently, also in non-supersymmetric cases, as we see from this list of papers. So we can evaluate this AJ function in perturbation theory, starting from this picture. We see that the first diagram here corresponds to the three-level term, where we simply connect all the J legs with three-level propagators. Then the two loops order is 0 in any superconformal field theory case. So we directly move to the two loops order. Here we can distinguish these two different classes of diagrams. In particular, they are different based on their multiplicity factors. In this case, the two loop corrections are inserted between two legs among this J. So the multiplicity factor here is J over 2. Instead, this class of diagrams corresponds to the two loops correction of a single propagator. So here we have J ways of inserting this diagram here. And now we evaluate this function in this J going to infinity limit, keeping lambda fixed. And we get that only this first class of diagrams is kept in this J going to infinity limit, since this class of two loops corrections of a single propagator is subleading as 1 over J. What do we learn? We learn that the J going to infinity limit selects those diagrams that involve the maximal number of legs. And this is true also for higher orders in perturbation theory. The crucial point is that the multiplicity factor is our guideline, which allows us to distinguish the classes that are kept in this limit and the classes that are not. And in our n=2 cases, it turns out that the leading order in J selects the maximally non-planar diagrams. Here we see two examples at 2 loops, at 3 loops order. And here it is quite intriguing, the fact that this J going to infinity limit selects precisely the dual class of Feynman diagrams with respect to the usual large N limit. Such duality between the roles of N and J naturally arises at the level of the n=2 matrix model. So in n=2 theories, a correlation function like this one on flat space can be mapped using a localization procedure to a finite dimensional integral of this shape. This is the so-called Pestum matrix model, where the integration variable A is a n by n Hermitian matrix. And in this setup, using standard matrix model techniques, it is possible to evaluate this observable AJ at large N, number of colors. But it has been formalized in this paper in 2019 that using a special matricial trick, it is possible to map this matrix model to a different matrix model of a Wishart-Laguerre type. In this case, this integration variable W is a J by J positive matrix. And in this case, it is possible to evaluate this observable and also many others at large J dimension. I stress the fact that on this matrix model, many interesting results can be obtained, and we discuss all of them in our paper. So we can make a brief summary. We understood that gauge theories admit not only the usual Toft limit for the number of colors n going to infinity, but also this large charge double scaling limit, which is obtained by taking the charge of operators j going to infinity. Our main result in n=2 theories is that whereas the usual Toft limit selects the planar diagrams, this large charge limit selects the maximally non-planar diagrams, that is, the dual class of Feynman diagrams. In the future, it would be definitely interesting to understand if there exists a string theory interpretation of this large charge. On the same line, there exists this nice analogy between the large N and the genus expansion in string theory. Secondly, it would be interesting to see if our findings can be generalized to other classes of quantum field theories, for example, also non-supersymmetric cases. For the moment, we are sure that in n=2 cases, this duality between the roles of the number of colors n and the charge j is nicely realized at the level of n=2 matrix models. And I would like to invite all the people to see also Azima Hassan's talk, who will be more concentrated on this specific part. We understood that n=2 theories can be seen as a natural playground to understand generic features of quantum field theories. So I would like to thank you all for the attention, and I invite all the interested people to contact me for further clarifications and discussions. Thank you.